the recording. So welcome everyone for the lectures. We start with the second part of the lecture by Filipe Joaquim on theory of neutrino masses and mixing. So please, Filipe, whenever you want, you can start.
Can you hear me?
Yes.
Okay, thank you very much. Good morning, everyone. I hope you had a nice weekend. So the outline for today's talk, I will end up discussing the three-level realizations of the effective neutrino mass operator that we have started on Friday. Then I will talk about some models of radiative neutrino masses and some examples of hybrid models, and at the end, very basic considerations about flavor symmetries. So if you remember, on Friday, we were looking at the three-level realizations of the Weinberg dimension 5 operator. So basically, we were looking inside the structure of the operator and try to find out what kind of new degrees of freedom we can add in order to generate the five-dimensional effective operator. So we have seen the case of the fermion singlets. If you remember, we defined the Lagrangian, then we integrated out the heavy degrees of freedom using the equations of motion. Then we have compared with the general structure of the operator, and we concluded that the effective neutrino mass matrix is just given by this famous formula here. And the last thing I said was that if M, which is the typical mass scale of these new degrees of freedom, is much larger than the electroweak scale, then neutrino masses are naturally suppressed, and this is the type 1 seesaw mechanism. So the way we arrived to this result was rather formal, because I used the equations of motions for the new R's, but usually what people do is to look at the full mass matrix of the neutral fermions. So let me show you again the Lagrangian, now writing explicitly the terms which I'm interested in. So we have y nu r bar, nu L, and this is the interaction with the neutral component of the standard model Higgs doublet. We have the Majorana neutrino mass term for the heavy nu R's. Then if you consider that the standard model Higgs doublet acquires a web, you can define the corresponding mass matrix for the Dirac Yukawa couplings. So remember that when I discussed the general Dirac-Majorana mass Lagrangian, we did it in this way. So I have defined the vector where I put the nu L's, which are the left-handed neutrinos from the standard model, then the the conjugates of the right-handed neutrinos, and we have defined this big matrix, which, if you remember, was 3 times nr times 3 plus nr times 3 plus nr matrix. So now in the case we are discussing for the type 1 seesaw, this mass matrix will just have this form, where this 0 in the 1-1 entry is here because at the beginning there was no gauge invariant interaction, which could actually give rise to a left-left neutrino mass matrix. So this is why this 0 is here. So we want now to somehow diagonalize this matrix and see how we can obtain the effective neutrino masses. So we have seen that this big matrix is diagonalized in this way. This VL is also 3 plus nr times 3 plus nr unitary matrix, and these M1, M2, Mn are the neutral fermion masses. So comparing with the general situation that I have discussed on Friday, the difference is that now I'm making some assumptions about the mass scales that are involved in the mass matrix. Remember, on Friday, this was completely general, and I didn't say anything about any possible hierarchies in these mass scales. But now I know that I'm considering the case in which MR is much larger than MD. So what I can do is the following trick. First, I perform a unitary rotation in such a way that I block diagonalize this matrix. And the result of this will be to separate the light neutrino sector with the heavy one. Okay. We can write this W matrix in this way. This is supposed to be understood as a power expansion of, in terms of these B matrices. And you will understand why people do this, because now I can try to find out which is the matrix B that bulk diagonalizes this matrix, and as a result, I also get the form of M nu and Mn. Okay, this involves a little bit of algebra, but the result is the following. So you see M nu is equal to this term here, which is nothing but the one which was obtained also when we performed the integration of the heavy degrees of freedom. And then you have also other higher order corrections in the seesaw expansion. And you can see from here, just by performing a rough estimation, that this term is actually much smaller than this one. For the heavy sector, Mn, which is the effective mass for the heavy degrees of freedom, is approximately Mr in the lowest order of the seesaw approximation, and also the other terms are negligible. Remember that here I'm always considering the type 1 seesaw in which Mr is really much bigger than the electroweak scale. Okay, so at lowest order in the expansion, we have the same that we have found before, and for the heavy ones, Mn is equal to Mr. Now, for the matrix W, you can also find out, this matrix is important because it's the one which will help you connect the heavy and the light neutrino sector. So you can show that it's enough to go to first order in the expansion of these square roots, and you conclude that B, or B dagger if you want, is M-1 MD. Okay. So, but still don't forget that these two matrices, effective matrices, are not diagonal. You have to diagonalize them, but now it's easy because they are already separated. The full matrix is block diagonal, so you only have to look at how you diagonalize each block of the big matrix. So these are diagonalized in this way. So this we have seen already last time. So when you diagonalize M nu, you get the light neutrino masses, and when you diagonalize Mn, you get the heavy ones. Okay. So what about the full matrix, which actually characterizes the mixing between the neutral fermions, and also the mixing between the charged leptons and the neutrino mass eigenstates? So on Friday, we have seen that the structure, the general structure, is this one. Okay. But by that time, we didn't make any assumptions about the size of the mass scales. But now the full matrix has been diagonalized, block diagonalized. Okay. The neutrino mass scales are now separated due to the seesaw hierarchy, and the active sterile mixing is not arbitrary as a consequence of these two facts. So if now ask you, how do you expect the heavy light neutrino mixing to be? Would you say it's large, small, or very small? So let me put here A, B, and C. Okay, can you see it?
Yes.
Okay, perfect. Okay, so we have around 30 answers. Okay, so I think I can stop. So most of you answered very small, and it is correct, because if you remember, the matrix which was controlling the heavy light neutrino mixing was B, is the matrix B. And you can see it here. Now that I have replaced, now that I have written this, the large the mixing angle, the full mixing mixing matrix in terms of the matrices which diagonalize the charge lepton mass matrix. Remember that I told you last time that we also have to account for a possible diagonalization of the charge leptons. Actually, I could have started in the charge lepton with in the basis where the charge lepton mass matrix is diagonal, but in this case, it's more general. So you see that the block which controls the heavy light neutrino mixing is this one. Okay, so VL and UN can be unitary matrices. They don't necessarily have to be small, but B is very, very small because it's of the order of MD over MR. And if you remember, if we consider order 1 Yukawa couplings between the lepton doublets and the nu Rs and the Higgs of order 1, you will end up with the MR scale of the order of 10 to the 14 GeV. So this is really, really, really small. Okay, so what about the neutral current and charge current interactions? How will they be in this case? So in the type 1 CSOF framework, and leaving only the first term in the expansions also in those B matrices, we have, for the interactions with the Z boson, we have the following. So you see here that I have U nu dagger 1, the 3 by 3 identity matrix minus B dagger times U nu. Okay, so this is not a unitary matrix, but you see that when B goes to 0, okay, if you increase arbitrarily the MR scale, B goes to 0, you recover unitarity. So actually this BB dagger, it's the entries of these matrices is what is controlling non-unitarity effects in these interactions. The same, something similar for the heavy sector, which is not very interesting. And again, for the heavy light neutrino mixing, you see here that B is always appearing. Okay, again, if B is 0, now heavy light neutrino mixing is obviously 0 because the neutral and the light and heavy neutrino sector decouple completely. So for the charge current interactions, you see again that you have non-unitarity effects. You have VL dagger U nu. If B goes to 0, you recover the expression for the lepton mixing matrix that we got on Friday, which is just the misalignment between BLL, which is the matrix, the matrix which diagonalizes the charge lepton mass matrix on the left, times U nu, which is the matrix which diagonalizes the neutrino mass matrix. Okay, so and here you also have mixing between the charged leptons and the heavy neutrino states. Again, controlled obviously by B, because if B goes to 0, obviously the charged leptons do not interact with the heavy neutrinos also. Okay, so if we focus only on the light neutrino sector, and if we use the expansions we found before, we can define this matrix N, which is just another way of writing this. So if you compare this with this, you see that this epsilon matrix here will be BB dagger. And n and dagger will be approximately the identity matrix minus epsilon, and dagger n will be this combination here. And now if you rewrite the charge and neutral current interactions, you have this. So you see here that in the interactions with the W are controlled by this matrix NJK, which is just this one. Okay, obviously if epsilon goes to 0, this is unitary. You have a unitary matrix here, and the interactions with the Z boson are given by this combination n dagger n. And again, if epsilon goes to 0, this goes to 1, and we recover the standard model situation. So now the question is, how constrained are these non-unitarity effects? Actually, they are pretty much constrained. There are several ways of looking and several processes that we can look at to constrain these non-unitarity effects. The most stringent ones come from lepton flavor violating decays, like mu E gamma, for instance. So you see here some limits taken from this paper. If you want to know the details, you can go there, and the processes are very well discussed, and they explain how they extract these limits. So you see that this is square root of epsilon. And for instance, for the E mu entry, so for the interaction where you have an electron and a muon, this is smaller than around 4 × 10⁻³ . So this is square root of epsilon. So epsilon will be around 10⁻⁵. So you see that there are some of the entries of these non-unitary matrices are pretty much constrained. But we know that for the type 1 seesaw, this epsilon is given by this combination. And if we just do an order of magnitude estimate, this will be md² over mr², which is roughly m nu over mr. So in the type 1 seesaw, this is really small. So there is no natural way to probe these kind of numbers in the vanilla type 1 seesaw. So basically, this means that with the scales that we have discussed for the type 1 seesaw, these non-unitarity effects are negligible. Okay, so let's count the parameters to see if actually we can get some information about the original Lagrangian, taking into account what we know from low energy neutrino data. So the idea and the question is, we know what are the mixing angles, we know that what are the neutrino mass square differences, and the question is, can we reconstruct the original Lagrangian or the original parameters from what we know from neutrino oscillation experiments? So let's count the parameters. Let me go to the case in which ML and MR are diagonal. So I can always diagonalize independently both these matrices. And in MR, I will have the NR heavy neutrino masses, or the NR heavy eigenstates. And for Y mu, I will have 3 times NR times 2, because they are complex in general. I can remove 3 phases, and in total, I will have 7 NR minus 3. Okay. So now the question is, if the effective neutrino mass matrix is given by the seesaw formula here, so forget about other possible corrections that may be at the quantum level, but I'm only concentrating now at the 3 level. So if m nu is given by this, what is the smallest number of right-handed neutrinos that I must add to the standard model in such a way that I am able to accommodate neutrino data. Okay, so let me do it here. A, B, C, and go. So how many of these guys do I have to add in such a way that I can not explain, but accommodate? Okay. Remember that when I say accommodate neutrino data means 3 mixing angles that we know that are non-zero and 2 delta m squares. Okay, so we have a tie. Okay, so let me stop. So you see 11 for A, 19 for B, and 5 for C. Actually, the answer is B. Okay, and this is quite easy to see. If there is only one right-handed neutrino, and if you construct the effective neutrino mass matrix with this, you will end up with two massless effective neutrinos. So with two massless effective neutrinos, you cannot have two delta m squares that we know that are non-vanishing. But with nr equal 2, then the effective neutrino mass matrix is a rank 2 matrix, but you still have one massless neutrino. But as I told you on Friday, this is compatible. This is perfectly compatible with data. And in this case, when you have two right-handed neutrinos, we have 11 parameters in the original Lagrangian. You see it here. So 7 times 2 minus 3, 11. And this is to be compared with 7 low energy parameters. So 3 mixing angles, 2 masses or 2 delta m squares, because in this case, the number of delta m squares and the masses coincide, because one of the neutrinos is massless. And we have two phases, one Dirac phase and one Majorana. And there is only one Majorana phase, because since you have one massless neutrino state, you can remove one of the two Majorana phases that we had in the general 3 neutrino case. So this is some people like to call this version of the seesaw the minimal type 1 seesaw, which is obtained from a standard model extension with two right-handed neutrinos. Okay, so the type 1 seesaw was, this is what we got when we are looking at the possible contractions of the couplings in the Weinberg operator, of the couplings of the lepton doublet and the Higgs, and when we chose the 1-0 combination, okay? But we have seen that there is another possible way of, another possible direction, which is to take advantage of the triplet contraction, okay? So remember, 2 plus 1 times 2 minus 1, this is SU2, this is hypercharge, gives 3, 0 plus 1, 0. So when we look at the 1, 0 case, we get the type 1 seesaw, because we have we need to add singlets, neutral fermion singlets. And now, for the case of the triplet, we will do the same exercise as before. So here you have the phi L combinations in the triplet. And now we need to connect these two sides of the diagram, adding something in such a way that each of the vertices is invariant under the standard model gauge symmetry. And you can convince yourselves very easily from what you know from quantum mechanics, for very basic quantum mechanics, that the only possibility to do this is to add another triplet. But this time it has to be a fermion. So you add fermionic triplets. And the algebra in this case is a bit more complicated because now we are working with triplets and not with singlets. So it is convenient to work with the charge eigenstates. You can show that if you want an hypercharge 0 triplet, you will end up with charge eigenstates which are neutral or plus or minus. Okay, it is also convenient to use the SU2 the SU2 writing of the triplet. You write the Lagrangian. Now you have to be careful because the covariant derivative, of course, is not as trivial as in the case of the singlets, because the triplets do not transform trivially under SU2. Then you have the interactions of the triplets with the lepton, the standard model lepton doublet and the Higgs doublet, and then you have a mass term for the fermionic triplets. Okay. Now you can again do the exercise of integrating out the triplets and compare with the Weinberg, the general form of the Weinberg operator. I leave it to you as an exercise, but at the end you will see that the coefficient of the dimension 5 operator is y sigma transpose, the inverse of m sigma y sigma. Now you see this is very similar to what we had for the type 1 seesaw, where the couplings with the singlets, lepton doublets, and the Higgs are now replaced by y sigma, and the mass matrix MR is replaced by M sigma. And this is the type 3 seesaw. Okay, so I've jumped type 2 because type 1 and type 3 come from the same type of contractions of the phi's and the L's. Again, we can do this looking at the full mass matrices. You will see that now there is something slightly different, not for the neutral sector, but for the charge sector, for the charged lepton sector. To see the full mass matrices, it is convenient to define the Dirac field for the new charge states, which I will do it in the following way. So it's sigma plus R conjugate plus sigma minus R conjugate. Obviously, this is not a Majorana field because it's charged. We can define, as in the case of the type 1 seesaw, I can call MD as y sigma v over square root of 2, because this actually comes from the coupling with the standard model Higgs doublet. Again, I can also call ML the charge lepton mass matrix, which comes from the coupling with the Higgs. And at the end, for the neutral fermion sector, and defining this vector in this way, where I put the standard model nu L's first, and then the n sigma neutral fields after. And if I do the same thing for the charge leptons, I put the standard model charge leptons here and the new charge lepton states afterwards. I can write the mass matrices for the neutral and the charge lepton states in this way. So M nu is very similar. It has actually exactly the same form as for the type 1 seesaw. The only difference is that MR is replaced by M sigma. But now ML, you see that the charge lepton sector is not as trivial as in the case of the type 1 seesaw, because in the case of the type 1 seesaw, we were not adding new charged fields. And now we are actually adding them, and not only we add these new states, but they also mix with the standard model charge lepton field. So there will be mixing among the ELs, which are the standard model states, and the new heavy ones. Now again, we can do the same exercise as for the type 1. The result will be exactly the same, where now MR is replaced by M sigma minus 1. Okay, and also the counting of parameters is very similar to the type 1 seesaw. Okay, so what about the charge lepton masses? For the charge lepton masses, it is convenient to look at the matrix ML dagger, because this is an emission matrix and it's only it's rotated by a single rotation. So I call this rotation WL. You may do the same exercise as before. Define the matrix F, diagonalize in blocks, and you will end up to the conclusion that you will have an heavy sector and a light sector. The light sector will be approximately given by ML dagger, which is the mass matrix that we are used to, plus corrections which are much smaller than these ones if M sigma is much larger than MD, as we are assuming. Now, for the heavy charge lepton sector, we get M sigma dagger plus corrections, which are supposed to be also much smaller than this term here. Okay, so you see that the differences regarding the mass matrices are not very significant. In the charge leptons and neutral current, the charge and neutral current interactions are now a bit more complicated, because you will also have non-unitarity effects in the charge lepton sector. But the conclusions are not much different from the type ones you saw in what concerns the possibility of seeing non-unitarity effects, because again, M sigma, this scale is much, much larger than the other scales involved in the problem. Okay, so we have seen already the two possibilities that we can get when we look at these the contraction of the phi of the standard model Higgs doublet field with the lepton doublets. So now we have to look to at the other possibility, which is to look at the LL combinations. Okay. So when I do LL, I'm actually doing the product of the 2 minus 1 times 2 minus 1, which gives 1 minus 2 singlet of SU2 with minus 2 of hypercharge, plus a triplet of SU2 with hypercharge equal to minus 2. So the first possibility actually doesn't lead to anything interesting, because if you apply what you know from quantum mechanics, the singlet combination will be nu LC conjugate bar EL minus EL conjugate nu L, and this will not for sure lead to any neutrino mass term. Okay, this will be just an interaction with the charged standard model Goldstone boson. Now, what about the 3 minus 2 combination? So here we have, again, these diagrams that we had before, but now the legs are a bit in a different position. So here I have 3 minus 2, here again 3 minus 2, and you can easily convince yourself that the only way to connect these two sides of the diagram is to add triplets of SU2 with hypercharge 2. Okay, so our model is now the standard model plus n delta copies of these SU2 triplets. Now, question, what is the mass dimension of this coupling here? So 5 phi delta. Okay, so people are answering very slow. It's Monday morning. Okay, so let's stop. So most of you answered 1, but there is a significant number of people saying that it's that the dimension is 2, but actually it's 1. It's a scalar. So if it's these are 3 scalars, so dimension 3. So the coupling must have dimension 1. Okay, this is important because we will see later that this new coupling will actually be very important and will be responsible for some features which were not present in the type 1 and type 3. Okay, so again, this is a triplet of SU2. We can use the 2x2 way of writing the triplets. We also have to do some trick here because to match the transformation properties of the interactions with the standard model lepton doublets. At the end, the Lagrangian will just be the Lagrangian of the standard model, plus the kinetic terms, where, of course, we have now to include in the covariant derivative the term which is responsible, which have to do with the SU2 transformation properties and also the U1 transformation properties of the delta, because remember that now delta does not transform trivially in with respect to SU2, but it also carries hypercharge. Now the interactions with the lepton doublets are just LL delta, roughly. Of course, you must have these conjugates and bars in order to have it gauge invariant. But remember that this thing here is just L transposed delta L. Okay. But now, since you are adding new scalars, you must define the scalar potential of the model. So this is the most general form of the scalar potential with compatible and with the standard model gauge symmetry. And you see here the couplings that we were talking about before. So this is the coupling of the delta A with phi phi. Okay. This new mass parameter will be called mu A. Okay, so now we can decompose this interaction, and you see that there is at the end a term which involves the neutrinos, nu L, and the neutral component of the triplet. So now if this neutral component of the triplet acquire a vacuum expectation value in this way, we will end up with this term here. So you see that this which was a Yukawa interaction, just like the other ones in the standard model, now became a mass term. And this mass term is characterized by this Majorana neutrino mass matrix. So you see in the case where you have n delta triplets, you have to sum all the contributions which come from the coupling of each delta to the neutrino fields. And the mass scale involved in each of these terms is the vacuum expectation value of the neutral component of the triplet delta A. Okay, so the question is, what can we say about this vacuum expectation value of the neutral component of delta? So suppose that I say, okay, roughly m nu, the neutrino masses, are roughly some Yukawa couplings times the VEV of the triplets. And now I consider these Yukawa couplings of order 1. So this means that if I want m nu of the order, for instance, of 1 electron volt, I need these triplet VEVs to be of the order of the electron volt. Okay, so this is way much smaller than the electroweak scale. So another important issue regarding these triplets is that since they now transform non-trivially under the standard model SU2 group, if these deltas acquire a VEV, they will for sure contribute to the mass of the standard model W and Z bosons. And this is a problem because we know that these things are very well measured. And in fact, we know that if we add these triplets, we will have contributions to the raw parameter, which in this case are given by this. So I'm sure you have talked about this raw parameter during Andrew's talks, because this is a very important precision test of the standard model, and that you should check when you add new degrees of freedom. Experimentally, this is very close to 1. Okay, in the standard model is exactly 1, but experimentally there is this result here, and this tells us that the VEVs of the triplets must be very small, and if roughly this should be below few GeV. Okay, so the question now is it natural for neutrino masses to have, for instance, the VEV of these triplets of the order of few GeV? And I would say no, because if you have these triplet VEVs of the order of GeV, then to explain masses, neutrino masses, for instance, of the order of 0.1 electron volts, you would need very, very small Yukawa couplings. So you really need to go below for the scale of these triplet VEVs. Okay. So we will discuss later whether if this is natural or not in this context. So I've told you that the neutrino mass matrix is just a sum of the several contributions coming from each of the triplets. But now the question is, what is the minimal number of triplets that we must add to accommodate neutrino masses? So let me stop this one. So A, B, and C. Okay, so okay, so let me stop. There was a question, yes, we expect, but I'm doing a rough estimate, okay? So if you won't consider the 2 sigma or interval. This was just an illustration, okay? In fact, you expect, you are right. So the question was, in the previous slide with the corrections to rho coming, don't we expect rho less than 1? It is true, but I'm just doing a rough estimate here, okay? So if you won't consider the level of sigmas that you need to go beyond, below 1. Okay, so the answer, which I don't have it here anymore. So there was, most of you answered 1, but there were still people saying 2 and 3. So the correct answer is 1, because now you look here, this Yukawa coupling is a 3x3 complex matrix, which is symmetric. And you actually only need one of these triplets to get, in general, 3 neutrino masses, 3 mixing angles, and also 3 phases. So let me take that example, only one triplet, because this is the minimal model that we need to accommodate the data. And this is the potential. These are the fields written in terms of their constituent fields. So what you have to do now is minimize the potential, compute the scalar mass spectrum, and assume that m delta square is much smaller than v squared, which is much smaller than u squared, okay? And you end up with the conclusion that the triplet VEV is given by approximately by mu v squared over m delta squared. So you see that there are two mass scales here suppressing this induced VEV for the neutral component of the triplets. This mass scale for the triplets and also this mu parameter, okay? Then you have the scalar mass spectrum, the neutral scalar mass spectrum. You will have one state which whose mass is around the electroweak scale, and another one with the mass with the typical mass equal to m delta. Okay, and this is actually the what is in the basis of the type 2 seesaw mechanism. There is somehow an induced VEV for the triplet, which is triggered by electroweak symmetry breaking, but the suppression of this VEV is not only by the large scale m delta, but also by this mu parameter that can be small. Okay. So let me compare these three types of seesaw regarding some important issues. So we have seen that in the type 1 and type 3 seesaw, the effective neutrino mass matrix is given by this combination here. Okay. So you have basically two scales involved in these two versions of the seesaw, the electroweak scale and the scale of the heavy degrees of freedom. So you see that if you want to lower the scale and you want to keep the effective light neutrino masses at a certain level, if you want to lower the scale, you will always have to go to smaller and smaller Yukawa couplings, okay? So basically, if you want to m of the order of 1 TeV, the couplings become so small that you start asking yourself if this is natural or not. Because if you want very small couplings, then probably you could also consider the Dirac neutrino masses. Now, on the other hand, on the type 2 seesaw, neutrino masses depend on two scales, mu and m. Now you see, if mu is small, m can be lowered without touching, let's say, the Yukawa couplings. Now the question is whether having this mu parameter small is natural or not. And what people usually advocate is that yes. Okay, why? Let me consider the following. So remember that the mu scale is the, associated to the coupling between the phi and delta. So let me assign the following lepton numbers to the field. So phi as lepton number 0, the charge, the lepton doublets and the right-handed singlets have 1, and delta has -2. Okay, so you see that this term here violates lepton number by 2 units. Now, this mu term breaks lepton number, and if it breaks lepton number, it can be naturally small in the 't Hooft sense. Okay, it's the only term which breaks lepton number. And what does it mean? It's naturally small in the 't Hooft sense. So 't Hooft, some years ago, already 40 years ago, made the following conjecture, which says that at any energy scale mu, a physical parameter or set of physical parameters alpha mu is allowed to be very small only if the replacement of that parameter by 0 would increase the symmetry of the system. Okay, in what follows, this is what we mean by naturalness. So you see that this is exactly what is happening here. If I turn off this parameter, if I put it to 0, I immediately gain a new symmetry in the Lagrangian, which is lepton number. Okay, and so this mu parameter is small in the TOF, is naturally small in the TOF sense. Now, another feature of which is important has to do about the reconstruction of the parameters. So in the type 1 seesaw, we have seen that it's not possible to reconstruct the high energy parameters from the low energy data without making additional assumptions. In the type 1 seesaw, the flavor structure of the neutrino mass matrix is the same as the one of the original Yukawas. You can see it from here, okay? So basically, the unitary matrix that diagonalizes M is the same that diagonalizes the Yukawa coupling matrix which you had in the original Lagrangian. So this is very nice because these couplings are involved in many other processes which occur in the type 2 seesaw mechanism, like lepton flavor violating decays. And in general, these branching ratios may be related with each other and can be written in terms of the low energy neutrino parameters that are measured in neutrino oscillation experiments. So also we have seen that in the case of type 1 and type 3, non-unitarity effects are very small. There is no chance to observe extra effects like rare decay experiments, colliders, etc. if you have such a high scale for the new degrees of freedom. And also the mixing with the standard model leptons is highly suppressed. Now here, since the triplet mass scale can be lowered, it is more likely that we could observe new physics effects other than neutrino masses. Okay, for instance, at the LHC. Okay, so the question is now, can we find other realizations of the seesaw mechanism which share this nice feature of having an extra mass scale that could also contribute to the suppression of neutrino masses in such a way that I can lower the scale of the new degrees of freedom? And the answer is yes. This is the inverse seesaw. I will be very fast on this. So we add extra singlets besides the ones that I was adding before. Now I have new mass terms for these extra singlets, which are these ones, which violate lepton number, these ones, which violate lepton number also. And okay, maybe this one I will answer myself. So for the mass terms in blue, delta L is equal to 2. Okay, so these terms violate lepton number. And you see that I'm introducing new scales in my problem. So now, upon electroweak symmetry breaking, I have a Dirac mass term from here, from the old couplings of the standard model leptons with a new R's. I can define again a big mass matrix, which will be now 3 plus an R plus an S squared symmetric matrix, where an S is the number of these singlets, new singlets that I have added. I can assume, just for simplicity for now, that this term here is 0 and keep only this one. Again, I apply the same procedure that I've done before, block diagonalize the matrix, and at the end, the effective neutrino mass matrix will be this one. Okay, so you see MD, MR minus 1, MS, MR minus 1, MD, which is approximately, or roughly, it goes with mu MD squared over M squared, where mu represents this new mass scale here. And this is called the inverse seesaw mechanism. Okay. Now, why is this appealing? It is appealing because now you see that with this new mass scale, I can lower this M scale here, which is the scale of the new R's, let's say. I can lower this scale and lower mu also, and keep the neutrino masses as light as I want, okay? And not touching in this MD, that is, the Yukawa couplings will be order 1, okay? So this is what is written again here. So now, when we compare with the case of the type 1 seesaw, something interesting comes up, and it has to do with the fact that the non-unitarity effects in this case are still controlled by md squared over mr squared. So you see, since now I can lower the scale of mr and have at the same time neutrino masses low by lowering the parameter mu, I can have now sizable non-unitarity effects, okay? So for instance, if the couplings are of order 1, mr is of the order of 1 TeV, and mu is 0.1, so we expect the typical scale of mu to be of the order of the electron volt, okay? So this is the size of the mu parameter that I need, in such a way that I can lower the scale to 1 TeV and keep the couplings, the Yukawa couplings Y nu at order 1. So this means that epsilon will be approximately equal to 10 to minus 2. So you see that automatically 10 to minus 2. So it's already excluded in some cases. You see that the square root of epsilon will be 0.1. So, and I have here constraints which tell me that the square root of epsilon have to be smaller than 10 to the minus 3. So, but if I now lower a bit the Yukawa couplings to order 10 to minus 3, which is not that small, and I lower the scale mr at 100 GeV, then I get epsilon of the order 10 to minus 6, which is safe, taking into account these constraints, okay? So the inverse seesaw actually is the perfect template for low-scale neutrino mass mechanism, and it has a lot of phenomenological consequences, like lepton flavor annihilation, electric dipole moment, G-2, collider searches, etc. I believe that Sasha will tell you more about, at least about lepton flavor annihilation from the effective theory point of view. So now the question is how to obtain such low values of mu in a natural way, because if we need mu of the order of electron volt or keV, then you should better think on some mechanism which suppresses this this parameter in the scalar potential. Now there are some ideas. Okay, this is just one proposed by Federica some years ago. You just add some extra fields. You prevent any field which may acquire a VEV to couple with the new singlets S. Here it's capital S, but these are the same small are the same as the small s that I introduced before. Then you construct the scalar potential. You minimize the potential, and now you say that, okay, these deltas, which are coupling with the new singlets, do not acquire a VEV. Okay, why? Because if they acquire a VEV, you have to explain why this VEV is very small, or maybe consider very small Yukawa couplings, and you don't want that. You just say that this delta, okay, which is a singlet of SU2, it has lepton number -2, so it can couple with SS. It does not acquire a VEV. Only delta tilde, which has lepton number -1, acquires a VEV. If you want this specific vacuum configuration where the Higgs is VEV VW, this phi field V phi, and the delta V delta tilde and delta does not have a VEV, then you must impose these conditions for the other parameters in the scalar potential, which come from the minimization conditions here. Okay, so you see, since delta is VEVless, there is no mu term generation anywhere, okay? Because this does not acquire a VEV. However, we can see if this term is generated at higher orders, okay? So for instance, is there any dimension 6 operator of this kind, S delta tilde in such a way that when delta tilde acquires a VEV, this is actually a mass term which is suppressed somehow also by some scale lambda. This actually happens at the 2-loop level. So you see here, this effectively is an S delta tilde operator. And now when delta tilde acquires a VEV, this actually reduces to a mu term that we had in the original Lagrangian. So how small is this mu term? Okay, so if you make some reasonable assumptions, you will end up with a result that mu can be of the order of 1 keV, okay? So you see, there are other options, there are other ways of doing this. This was just one example that I remembered. And just to illustrate that one can actually get naturally small mu parameter that we need to explain the smallness of neutrino masses with relatively low scale fermions entering into the game. So up to now, we have discussed models for Majorana neutrino masses, which are generated at the 3 level. Well, except for this case that I have considered a specific example where the mu term is actually generated at the loop level. But now it is important also to see whether there are realizations where the lowest order contribution to neutrino masses comes actually at the loop level and not at the 3 level. Okay, so again, I'm interested in realizations of the Weinberg operator, in which its origin is not at the 3 level as we have seen for the type 1, type 2, type 3, and the inverse seesaw, but at the loop level. So let me just discuss very briefly the one loop case. All the one loop topologies have been classified in these papers. Okay, so these are called genuine one loop topologies, and by genuine it means that only diagrams starting from n order loops contribute to neutrino masses. So these are the lowest order contributions to neutrino masses. So this means that there are no 3 level contributions. This is what I mean by genuine one loop topologies. These were classified in these papers. You have here the topologies. These dashed lines can be either scalars or gauge bosons, okay, the internal dashed lines when possible. There are others, but these you can show that either they cannot be realized by, for dimensional reasons. Other ones are just correction to 3 level seesaws. For instance, if you look at maybe this one, you can see that probably the type 2 seesaw contribution at 3 level would be already there, and the one loop would be just a correction. Then you have divergent contributions, which again just give a correction to the 3 level, because actually to cancel these divergences, you need the counter terms, but the counter terms are already in the 3 level couplings. So this, when you sum up, this will just be a correction to the 3 level contribution. So this means that you cannot forbid by a symmetry the 3 level contributions as in these genuine topologies. Okay, some example. The Z model is a famous example of a radiative neutrino mass mechanism. So we have 2 Higgs doublets. We have a charged scalar. This charged scalar transforms as 1, 1, 2. So it's a singlet of SU2 and there's hypercharge 2. These are transformed just as the standard model Higgs doublets. Now here you may be surprised at why doesn't the neutral component of H2 has a VEV, but I have done a trick, which is to go to the Higgs basis, where one of the doublets is VEVless. So originally, this could be called phi1 and phi2. Okay. You write the scalar potential. You minimize. You compute the scalar mass spectrum. You get this. Okay. So I will not go into details. If you want to see a very detailed study about this, a recent study about the Z model, you can look at this paper. Now you can also write the Yukawa interactions with the doublets. So you see here they are written as in terms of phi1, phi2, so the original doublets. So you have L bar phi1 ER. So these are just like the charge lepton Yukawa terms, or the lepton Yukawa terms of the standard model. And you have these extra couplings here of L tilde bar FL H plus. This H plus is the charge scalar singlet that we have added. Now you can see that in this case you cannot generate the 3-level neutrino masses. The lowest order contribution is this one, and this is an example of a topology of this type that was in the list of these genuine one-loop topologies. The effective neutrino mass matrix is given by this. This S2 phi is an angle which tells you how the charged scalars mix among themselves. If you define some extra quantities like ME, this mass scale key, or tangent beta, which as usual is the ratio of the VEVs, and this is the mixing angle which enters here, you can ask yourselves if it is natural or not to have small neutrino masses. And again, yes, because you may do a lepton number assignment in such a way that if mu is equal to 0, lepton number conservation is restored and neutrino masses vanish. Why? Because if mu is equal to 0, you see that immediately the charge scalars do not mix. And if they do not mix, then the neutrino masses are 0 because they are proportional to this mixing among the charge scalars, which is given which is given by mu. So this model has many interesting phenomenological aspects, and again you can see it here in this paper. Another interesting case is the scotogenic model. This is very popular by now. In this case, we add an extra doublet, scalar doublet to the standard model, but it's not exactly the same as the standard model doublet, because now we introduce a Z2 symmetry, and this eta doublet is odd under the Z2 symmetry. Okay, and we also introduce new fermions, which are also odd under the Z2 symmetry. These are usually called dark. It's usually called the dark sector, and you will understand why. So what you can do is to write a mass term for the singlets, a coupling between the singlets L and eta. And now you write the scalar potential, and you consider the case in which eta does not acquire a VEV. So again, this is very similar to the inert 2 Higgs doublet model, where you have two doublets, but one of them does not acquire a VEV. So what happens in this case is that the lowest order contribution to neutrino masses is given by this diagram here. Okay, this is an example of a topology of the type T3. And you see that the crucial parameter here is lambda 5. Lambda 5 is this coupling here among H, which is the standard model Higgs doublet, and eta, which is the inert doublet. So you can work out the neutrino mass matrix, and you see that this depends on a loop function of the new scalars, the CP even and the CP odd scalar. And you immediately see something interesting, which is if lambda 5 is equal to 0, these two scalars are degenerate and m nu is equal to 0. Okay. So the point is now again, is it natural to have lambda 5 equal to 0? Yes, because again, you can assign lepton numbers in such a way that when lambda 5 goes to 0, you gain again a lepton number. Okay. So these are just some limits which you can look out afterwards. There is some interesting phenomenology. For instance, there is lepton flavor violation, radiative decays like mu e gamma, or mu into 3 electrons, mu e conversion in nuclei. You can see more details in this paper by Avellino and Toma. And now you can actually think of some scenarios where you mix 3-level and radiative mechanisms. So this is the case of a Scotto-Seesaw, which I particularly like. This was proposed recently by Jose Raul and Nicholas, I think. So what you do is you take one copy of fermion that you had in the Scotto-Seesaw. You take one copy of singlet, fermion singlet that you have in the type 1 seesaw. You give these Z2 assignments to the fields. So the dark, let's say the new R, which is the same as the one that we were adding in the type 1, is even, the doublet eta is odd, and F is odd. And you will have two contributions, one coming from the type 1 seesaw, which is 3-level, okay? And if you only have this contribution, you will only have one massive neutrino at the end. But now you also have the Scottogenic contribution, okay? So usually what is said, what they said in the original paper is this: the type 1 seesaw gives you the atmospheric mass scale, and the Scottogenic mechanism gives you the solar mass scale. So you can write again the scalar potential. There is this nice way of writing the full neutrino mass matrix. You see here in the 1-1 position where you would have the left mass, and you have the Scottogenic. Here you have the mass matrices of the seesaw, the type 1 seesaw. And now if you block diagonalize, at the end you have the sum of the two effective contributions here, and here you get the heavy sector, which is just the one as you had in the type 1 seesaw. So at the end you see that the effective neutrino mass matrix is the sum of two contributions, one coming from the type 1 and one coming from the Scottogenic diagram. If you consider any of them alone, you cannot fit the data, because we know that if you consider one of these contributions only, you will end up with the situation where you have two massless neutrinos. So you can do some benchmark scenarios. There is, you can also study lepton flavor violation here. I will not go into too much detail in this thing. So up to now, I have discussed only neutrino mass mechanisms where at the end neutrinos are Majorana. And this is interesting. Why? Because, okay, we have seen that there is no problem with Majorana spinors with Poincaré symmetries of the standard model. Actually, there is this strong argument that Majorana neutrino masses fit nicely if you look at the standard model in an effective theory approach. And we have also seen that if you add right-handed neutrino fields to the standard model and you don't do anything else, then at the end, the mass eigenstates turn out to be Majorana. So what about Dirac neutrinos? Why don't people like Dirac neutrinos? Well, the general argument is that if neutrinos are Dirac particles, and if they acquire their mass in the same way as the other elementary fermions, then you would need very, very small Yukawa coupling. So if you are interested in neutrino masses of the order of 0.1 electron volt, you would need Yukawa couplings of the order of 10 to minus 12. And this is way too small and much, much smaller than what we are used to. Also, it would also mean that the Yukawa couplings of neutrinos are much, much smaller than the ones of their SU2 partners in the doublets. But in any case, this theoretical prejudice may not be, and certainly isn't, nature's guiding principle. So that's why people have been also constructing models where you can have naturally suppressed Dirac neutrino masses. And this is the case, for instance, for Dirac seesaw. Okay, so what you want at the end is that you want to end up with some Dirac neutrino mass term, but you don't want to have this term here. So this Majorana type mass term for the new R's. Why? Because we know that we will, in this case, if both are present, we will end up with mass eigenstates that are Majorana. So first, I want to forbid this term, and I also want to forbid this term at 3 level. Because otherwise, if this couples, for instance, with the Higgs of the standard model, again, to give these very small masses, I will need very small Yukawa couplings, and I want to avoid that. So in order to forbid this mass term for the new R's, I can use lepton numbers, EN symmetries, whatever. You are allowed to use whatever you want. And then you have to somehow forbid this coupling nu L bar, nu R phi 0. Okay. So this is just an example. You can consider a pair of vector-like neutral fermions. By vector-like, I mean that the left-handed and right-handed components transform in the same way under the standard model gauge symmetry. So this is not the case for the other fermions in the standard model. So this transforms as a vector-like pair. And I will also add a scalar, a singlet scalar with hypercharge 0. So lepton number of the nu L's, nu L, nu R, and NL and NR is equal to 1. To forbid this term, which is nothing but this term here, I consider Z2 symmetry, under which nu R and S are odd, and then I can write the Yukawa and mass terms in this way. Okay. So you see there is no coupling between the lepton doublets and the new R's. And L and N R. And then when phi and S acquire a VEV, you will get this effective neutrino mass matrix. Okay.
Filipe, sorry to interrupt you. I think you disconnected for some moments. So
where did I stop?
If you could maybe repeat the last slide, I think.
So this slide.
Yes.
Okay, so I'm interested now in mechanisms for Dirac neutrino masses, where these Dirac neutrino masses are naturally suppressed. So we know that we have somehow to forbid this. We want a Dirac mass term, okay, but we want to forbid this one because otherwise we know that we will end up with Majorana neutrino mass eigenstates. So you can do it however you want, with U1L symmetries, Zn, flavor symmetries, whatever. And I'm giving here one example, which is an extension where I had to the standard model a pair of vector-like neutral fermions. So vector-like means that the left-handed and right-handed components transform in the same way under the standard model gauge group. Nu L and L have lepton number 1. So to forbid the coupling of the doublets with nu R and the Higgs, I consider that nu R and S are odd under a Z2 symmetry. Now the Yukawa and mass terms are this one. So you see you have a coupling of the lepton doublets with the Higgs of the standard model with the right-handed vector-like field. Then you have the scalar, this singlet scalar that I introduced, which will mix the left-handed vector-like with the nu R. And I have a bare mass term for the vector-like singlets. So I can now construct, as I did for the Majorana case, the full mass matrix, but now you see that the term is a Dirac mass term, okay? So when the electroweak symmetry is broken and when S acquires a VEV, you see, and if you say that ML is just epsilon n times V, so this is of the order of the electroweak scale, MR will be of the order of the VEV of the singlet scalar, you will end up with the case where mu is approximately ml/mr over mn. So you see, if mn is much larger than mr and then ml, you get a seesaw suppression, but now your mass eigenstates are Dirac. Okay, so this is just an example. Actually, there are many other possibilities to realize suppressed Dirac neutrino masses. So up to now, we have seen that there are a lot of models for neutrino mass generation. What I've shown you is just a small sample of it. Actually, there are many dozens of models, depending on which fields you want to add. There are cocktail diagrams, penguin diagrams. There are whatever diagrams you may think of. But the question is that up to now, none of what I told you answers a very important question. So the question I asked at the beginning is that how can neutrinos become massive and how can you suppress their masses? Okay, so what we have seen is several ways of doing this. But the next question now is how can you explain this table? Okay. So I showed you this table before, and Michele in his lectures will discuss in detail how these results are obtained. But what I've shown you previously are just frameworks in which neutrinos acquire mass and their mass is suppressed. But they are not able from first principles to explain the neutrino mass and mixing pattern. Okay. For that, you have to do something else. You need a guiding principle to try to explain this. And the best guiding principle we know is symmetry. But now the symmetries that we must introduce are a different kind of symmetries. Up to now, we have seen the only symmetries I've told you about are symmetries which are gauge symmetries, but which act actually vertically in this generation chart that I showed you on Friday. But now I'm interested in exploring family symmetries, which are families which connect the different flavor the different flavor families of the leptons and possibly also quarks. Now these symmetries can be of many kinds, abelian, non-abelian, discrete, continuous, whatever. You have, I gave you an extensive list of reviews where this is explored in detail. I will not be able to discuss here, but also because this is a school and to touch some of these subjects, one needs some knowledge of group theory. And I believe there were no lectures of group theory in the school, so this is I believe it's a bit non-trivial to understand. So just very quickly, the question is why lepton, for instance, lepton mixing is what it is, and if you want to be even more ambitious, why lepton mixing is so different from the quark mixing. You know, the quark mixing is characterized by small mixing angles, but we know that lepton mixing, we have large entries in the lepton mixing matrix. So one of the simplest ways to do it is to consider abelian symmetries. Okay, so you just consider like electric charge, you consider flavor charges, then only the interactions which conserve these charges are allowed in your original Lagrangian. For instance, if you are thinking with, about interactions with the Higgs, only these vertices are allowed where the charges are zero, and this usually leads to texture zero mass matrices that you can actually test when you confront with the data. Then you can use something called flavons. You can consider insertions of flavons, give a U1 charge to the flavons, and explore a bit what happens with the higher order operators. And then when these flavons acquire a VEV, you will see that you will get hierarchical structures in your mass matrices. And this is called the Froggatt-Nielsen mechanism. Okay, so I think I don't have time to discuss this problem of discrete non-abelian symmetries, but I will be in my virtual office this afternoon if you want to just come out and we can chat a bit about these things. So some final thoughts, because I think my time is over. So we have seen that if we look at the standard model as an effective theory, Majorana neutrinos come out very naturally. However, we would like to have an experimental confirmation for this or not. You have seen that from Andrea's lecture that the most promising way to answer this question is by looking at neutrino stable beta decay. If you see neutrino stable beta decay and using the theorem that I told you about in the first on Friday, you immediately prove that you can use that physics to generate Majorana neutrino masses. Now, several models have been proposed for neutrino mass generation. I just gave you a small sample and those which are probably the most popular ones. But we would like to have access to the physics responsible for neutrino mass. And if actually this happens in nature, then neutrino masses must be generated by some of those mechanisms, low-scale mechanisms that I told you about. But the vanilla version of the type 1 and type 3 seesaw are not very natural if the neutrino masses are generated at low scales, or if the degrees of freedom that we are adding have masses which are not very far from the electroweak scale. So these manifestations of new physics can be either direct or indirect. Direct would be like some signals at colliders, for instance, at the LHC, and indirect would be something like in lepton flavor violating decays, non-universality, whatever. Those effects which are not actually looking for the new particles, but the effects of the existence of these new particles. Now, regarding flavor, the question is which is the right symmetry? And to answer, not to answer, but probably to reduce the number of possibilities that we still have available, maybe we need more precision in the neutrino, in the determination of the neutrino parameters, because there are still some issues that we need to just at least to throw away some possibilities, namely the octant of theta 2,3, the CP violating phases, the ordering of neutrino masses, and so on. And this is what I was telling here, because you see some of these flavor symmetries have lead to some predictions and some rules, which can probably be excluded when we will have more precise determination of these quantities here. Okay, so I think that's all. Thank you very much. And I'm now open for questions if we have time, which I think we don't, but.
Thank you, Filipe, for your very complete lectures. So let's see if anyone has questions.
Sorry that I'm 5 minutes late. So in any case, if you want to discuss, I will be in this afternoon. I was there on Friday and I discussed some things with a couple of people. So I'll be back this afternoon if you just want to come up.
Okay, very good, because I don't see, yes, probably there is a question in the chat.
There is one question, which is, what is the difference of integrating out and doing the perturbative expansion or the diagonalization of the mass matrix? Well, I would say that the integrating out is the more formal way of doing it. Okay, why? Because if you actually take the integrating out method and work, as I told you, in the path integral formalism, you can actually also obtain the quantum corrections to the theory. So we were only interested in the lowest order, the three level case. So that's why I used the equations of motion of the fields, because actually what you are doing is expanding the fields around the classical solution, the one which stabilizes the action. Okay, but if you want loop corrections, quantum corrections, you have to use the saddle point technique and actually work with the expansion of the fields around that solution. Now, the perturbative expansion gives you the same result at tree level. Okay, so now if you want to obtain the loop corrections, you have to do the calculation of the diagrams, of course. Okay, so the result, if you are only interested for tree level, you are only interested in the tree level result, then they are equivalent. Okay.
Okay, are there other questions for Filipe?
Yes. So.
Yeah, so it doesn't seem so. But as you said, so if you will be available in the afternoon, maybe.
Yes, I will. I will be there. Okay, so.
Okay, then thanks a lot again for these very complete lectures.